So this is a tutorial video for the stability analysis of steel structure on ABAQUS 2020 edition. So the objective of this modeling and analysis will be to generate the response curve for a 2D frame having two bays and single story. So a total of 5 analyses will be performed. Both linear and non-linear analysis will be performed, including material non-linear analysis, geometric non-linear analysis, and material geometric along with imperfection non-linear analysis will be performed. So buckling analysis will also be considered. So first of all, we will look at how to model and analyze buckling analysis on 2D frame. So here we can see that model 1 has been generated automatically. So as it is buckling analysis, so we will rename it to buckling analysis model BA, which means buckling analysis. So now we will create part. We will name it as part 1 model space. We can, as our structure is 2D, but as we are considering the minor axis bending of columns, hence we have to reorient the columns in minor axis. We will see it further on as we move along in the video. So that's why 3D space is compulsory for that. If you want to model the major axis bending, then 2D planar space can be also used, and the base features will be wire. That is the most simplest. Continue. So here we will sketch. First of all, we will sketch the general layout of our 2-bay single story structure. So now to assign the dimensions for the structure, we will go to add dimensions. We will select each of the member, and the height of story that we are considering is 12 feet, which is 144 inch. One thing that we have to keep in mind over here is that the units must be consistent throughout the modeling process. I am considering FPS system in which kips and kips and inches will be used throughout the modeling for the forces and lengths dimensions. You can also use metric system, but the main consideration that must be kept in mind is that the units must be consistent throughout. 144. The bay width I am considering is also 12 feet, which is 144 inches. So we can see here that the single story 2-bay frame has been the layout of 2-bay single story frame is complete. Now I will click on done, and the part is being generated. You can see here part 1 is generated. Now we have to create and assign material and section properties. We will go to create material. We will give it a name steel linear. As it is buckling analysis, since we have to consider linear behavior, so the Young modulus will be 29,000 for A992 steel. Similarly, 0.3 horizontal ratio. Okay. Now we will go to create section. We will assign category as beam. I am considering AISC standards. We will go here to profile, create beam profile. A W14 by 53 section is under consideration. You can use any of a section, but I am considering an I section. So here we have to enter the dimensions of the dimensions of the cross sections. So for W1453 section, the depth of member will be 13.9 inches. I, which represents the distance between centroid and the outermost fiber, in this case will be 13.9 divided by 2. The lower flange width will be 8.06. Similarly, the upper flange width, the lower flange thickness will be 0.66 inch. Similarly, upper flange thickness and the thickness of web will be 0.37. Okay. The material is assigned as steel linear, which we have earlier defined. Okay, now we'll go to assign section, and we have to select all the columns and beams and click on done. Section 1, and the section is assigned. Now we have to go to before that we have to reorient. So orientation must be defined. So we will select all of the beams and columns, and we will assign the default orientation. We can see here that the columns are arranged such that if lateral force is applied, they will bend along the major axis. So as we are considering the minor axis bending, so we have to reorient the columns to minor axis. Then we will again select all the columns, and we will replace -1 with 0 and the 0 with 1, and click enter. Okay, so we can see that the columns have been rotated at 90 degree, and now minor axis bending will be considered in analysis. Similarly, in assembly, we have to create instance. Click OK. Instance is created. Now we will go to step, create step. As we are performing buckling analysis, we will go to linear perturbation and buckle, then continue. So they request us for number of modes that we want the software to calculate basically. So I'll just consider first mode, and the vector will automatically be set by the software. Now step is assigned. Now we'll go to loads and concentrated force. Load 1 will be the vertically acting downwards of 100 kips load. So C2, which basically represents the direction of Y, will give 100 kip minus because it is acting downwards. Okay, so we can see that the load is applied. Similarly, a lateral load will be given to the left node F of 10 kips. Okay. So the loads are assigned. Now we will assign the boundary condition, create boundary condition. So we will select the bottom nodes and assign a fixed boundary condition. So we can see there that in this one all the rotation and translations are restricted. We will click it and continue. So fixed conditions are assigned. Now as we have considered a 3D space, so in order to avoid any deflections or rotations along the z-axis or out of plane, we will also restrict the whole frame in the z direction. So for this we will select the whole frame, and we will restrict U3, which is translation in Z direction, and UR1 and UR2 rotations will also be restricted. So loads and boundary conditions are assigned. Now we will mesh So first we will seed part instance. Okay, so before that you have to shift from assembly to part. Now the software will automatically approximate global size will automatically be estimated by the software. So we will keep it as default. Done. Now we will go to element, assigned element type, select the region, we'll select whole of the frame. We will shift geometric order to quadratic and OK. Now we will mesh part and click yes. So the meshing is complete. We can also see over here that each of the element is divided into 14 sub elements and the meshing is complete. Now before that we will go to job, create job, and name will be job 1. Okay. So before submitting we will go to assembly and set. We will right click on sets and create set 5. We can name it as set displacement. Continue, and we will select the left node. So what basically it does is that it will collect or save all of the displacement data of this node in set 5. So when we need to display the displacement data of the story, so we can get it from here and extract it. So click on done. So it is defined. Now we will go to assembly job and we will submit the job. It's running a bit slow, so so it's submitted. It might take a minute or two, so I'll be back when it's complete. So the buckling analysis is complete. Now I'll go to results. Here we can see the deformed shape of first mode, and we also get the eigenvalue, which is 7.56. This is basically the load factor, as we have applied a 100 kip load. So in order to get the critical buckling load for this, we'll multiply this by 100. So I have also created Excel sheet that has a number of bays equal to 2, number of story 1, and critical buckling load will be, the critical buckling load factor will be 7.568. I have given here a function which multiplies the critical buckling load factor or critical load factor with 100. So the critical buckling load PCR we have is 560 756.8 kips. So we can enter the critical load factor here, 7.568. Okay, so as we perform the other analysis, all the data will be extracted from ABAQUS and will be pasted over here, so that we can get the response curves. That will be LPF, which is load proportionality factor, versus displacement. So buckling analysis is complete. Now to perform the linear analysis, we have to copy, just so that we don't have to input all the data again. We'll make some changes in the linear analysis model. We have shifted to linear analysis model. Now we have to delete the previous buckling step and create a new step. That would be, in general, we'll go to static risks, continue, and we'll go to incrementation and set initial at 0.01, and the maximum increment will also be 0.01, and the number of increments will be 1000, just so that we get a smooth curve. Click OK. So the step is created. When a step is deleted and new is created, the loads and the boundary conditions must be defined again. So we'll again define all the loads. So node 1 will be -100 in y direction. Similarly, load 2 will be 10 kip. Also boundary conditions restrict all the degree of freedoms. And we will also convert it manually into 2D frame by restricting the z-axis translations as we did earlier. Now we will go to job and we will submit, first create new job, that is model LA. Okay. We will submit it. This will take some time because a total of 1000 steps or increments will be performed. We can monitor it from here just to see the progress of the analysis. So we can see that the increments has reached up to 131. It will increase 174. So it might take 2 to 3 minutes. So I'll be back when the analysis is complete. So the analysis is completed for linear analysis. We'll go to results. We can check the deformed shape and the deformations. Now to extract the LPF and the displacement data for the set that we have earlier defined, we will go to create XY data. We will select ODB history output, continue. Here we will go to load proportionality factor whole model. We will click on plot. So we can see that it is plotted. Now we'll dismiss that. We will go to temp and edit. So here in the Y column we can see all of the LPF data. So we can copy it from here. Go to C and we can paste it from here. So now to get the displacement data, we will again go to create XY data and go to DB field output. We continue. Now we will go to unique nodal in the position. Here we will select U1, which is the displacement in X direction. Now we will go to element and node set, and we had defined the set displacement earlier, so we will click on plot. So dismiss. Here we can see the data on the y-axis of displacement. We can copy it. Let's see. And we can paste it on the Excel. These will be total of 1000 data points. So as the analysis performed with maximum number of increment set to 1000, so that's why they are 1000 increments and 1000 points. So now to perform nonlinear analysis, we will consider both geometric and material nonlinear analysis. So first we will perform material nonlinear analysis. So we will copy the linear analysis model and we will give it a name, material nonlinear analysis. That will be MNA. We have to check its has shifted to MNA, and we have to make a minor change in the properties. So we have defined steel linear property. We will edit it and we can also delete it and create new. We will give it a name, steel non-linear. Now we have to give the linear inputs, that is same as earlier. Okay, and then we will go to mechanical and plasticity and plastic. So we will enter the plastic yield stress. First the yield stress, that is the yield the stress at the point of yielding. So and the plastic strain will be set to 0 and the yield stress will be set to 65 for plastic strain of 0.2. So you can see that here we are assuming a bilinear material having a stress of 50 yield stress and 65 ultimate stress. So we will click OK. So the non-linear property of material are added. Now we will just go to job and we will create a new job. Okay, and we will submit. So before that, as we have changed the name, we have to assign the section again. We can edit it. We will select steel nonlinear. Okay, dismiss, and over here we will assign section. Dismiss. Now we can go to job and submit the file again. It is running. So while the material nonlinear analysis is running, as we have extracted all the data for linear analysis, we can see here in the graph that the response curve is also linear, showing linear behavior. LPF is and displacement is linear. So the graph is already set so that it can take input data of x-axis and y-axis from the tables. So let's wait until the analysis is complete. So the material nonlinear analysis is complete. Now we'll go to results. We can see the deformed shapes. We will extract the data in the same manner as earlier. Load proportionality factor, plot. You can see the plot over here. We will click here and edit. We'll copy the data to the Excel sheet. ODB field output for displacement and node sets, set displacement plot. Take this place and we will extract the displacement data from here. So you can see that the the material nonlinear response curve is plotted over here, having a linear behavior initially and then showing non-linear behavior. So now we will minimize. Okay, it's minimize. So now we will perform a geometric nonlinear analysis having linear material behavior, but the second order moments and effects, or which we can call P delta effects, are considered. So for that we will copy the linear analysis model and we will give it a name, geometric nonlinear analysis, GNA. So it's shifted to GNA. So we have to make the small change. We can see that property is the same as linear, still linear, only the elastic property is given, so no need to change that. We have to make the minor change in the step. We'll go to step and edit, and we have to switch this NLGEOM to on. What basically it does is that it also considers the second order moments into the analysis, and the displacements because of the second order moments is also recorded. So this will be turned on and we have to run simply just create job GNA. Okay, and we have to submit it. So we can see that it's running. So see you after the analysis is complete. So analysis is complete for geometric nonlinear analysis. We can see here the deformed shape. Now we will extract the data in the same manner. Node set displacement plot. So the set displacement is compulsory to define, otherwise the results and the data cannot be extracted. So we can see that the geometric nonlinear analysis results are displayed over here. It has further reduced the stiffness of the frame. Now to perform a combined geometric and material nonlinear analysis along with imperfections, what we have to do is we have to change a bit of all the things. So we will copy the material nonlinear model and we will rename it to GMNIA, which means geometric and material nonlinear analysis along with imperfection. So the first thing that we have to change here, we can see that in the properties, the nonlinear properties, steel nonlinear is defined, which is okay. And what we have to do is, first we have to go to the buckling analysis model. So okay, first go to step and edit, turn this on so that second geometric nonlinear behavior is accounted for. Okay, so in order to include the imperfections, we have to edit keynotes of buckling analysis so that the first mode of the buckling analysis, the first mode shape is accounted for the deformations or the imperfections in the frame for the nonlinear analysis that we are performing now. So what we have to do is we have to type here steric node file u. So what it does is it saves the first mode shape, and later on we will access this data from the mode shape, and we will induce the first mode shape imperfections into the GMNIA analysis. We will click OK. So what we have to do first is to run the buckling analysis again, so that the first mode shape data is stored in the U file that we have just created in the keynotes. So we have to submit it again. Okay, while this is running, we have to edit the keynote of the GMNIA analysis as well. So over here we have to write steric imperfection comma file is equal to buckling analysis job. That was the name of the job was job 1, job -1, and after that we will enter step equals 1. Then we'll shift to the next line and we will enter 1 comma. So basically the imperfections that we are adding are h by 500, that is the total height that was 144 inch divided by 500, so that the here the 1 represents the first mode of the buckling analysis. So it will take the first mode shape and will induce imperfection of h by 500, which is in this case 144 divided by 500, that is equal to 0.288. Okay, so after this we will click OK. So we'll go to job. So the first the buckling analysis is complete. Now we just have to create job. continue. Okay, and we have simply just to submit the job. We can monitor it. Okay, so see you after it's complete. So the analysis is complete. So we will follow the same procedure for extraction of data. Critical node factor, node proportionality factor, and date, copy the data, and we can plot it over here. Similarly, ODB field output, node sets, node displacement plot, dismiss, we can edit, copy and paste. And similarly the CLF, we can just drag it down as it is a constant value. Buckling load is a constant. So we can see in the yellow line that GMNIA, geometric material nonlinear analysis with imperfection, have further decreased the stiffness of the frame. Hence, for slender member it's necessary, for to slender and imperfect members it's necessary to perform the nonlinear analysis and include the imperfections. So in this tutorial, basically it was an attempt to help you use ABAQUS in order to perform such analysis. You can see that these graphs just to give you so basically what I wanted to share was that these graphs are related to all these data. So on the x-axis it is taking the DLA or DMNA, which means displacement of material nonlinear analysis, and on the y it's taking the LPF from each of the column in each of the analysis. So that's all. I hope it finds you, it will help you in your basic knowledge of ABAQUS, and would help you to perform such analysis on ABAQUS. So this was just a 2-bay single story frame. You can perform any type of frame with any type of layout on ABAQUS using the same procedure. So thank you, that's all.